Basically, I've written this to serve as kind of a basic introduction to use it. And I've written it to include the information and the tools that I find myself using most often in my research. So if you want to learn more, or there are functions that I didn't cover that you need, there's some options that I've linked here in the notebook that are awesome for learning about ObsPy. And this is the official ObsPy tutorial and also the Seismo Live Jupyter notebooks for seismology, which include an ObsPy section among other topics. So we're going to start out working with some of the data files that I included on Slack that hopefully you've already downloaded, just to see how ObsPy can work with data. So these files that I provided are in the mini seed format, which is just a format for seismic data, but ObsPy can also automatically detect many other data formats such as SAC. So the first thing that we're going to do is just import the read function. So we do from ObsPy import read. Looks like my keyboard is fritzing out a little bit here. And so if you're not familiar with Jupyter Notebooks, you can just press the shift and return or shift and enter, and that will run that cell. And so now we've imported the read tool. So with the read function in ObsPy, you basically only need the path to the file on your computer. So there are additional options such as choosing like a start and an end time for the data you want to read in. But for this example, the file that I provided is only 5 minutes long. So we're just going to load it as is. And you can check out the other options on the documentation page that I've included here. So what we do is we read the data into a stream object. And so I'm just going to call this ST. And again, my keyboard is not wanting to cooperate today. We're just going to call this ST, and you can choose to name these variables other things if you want to, but if you keep them consistent with what I typed today, it'll be the same in the full notebook later, so that might be useful if you're trying to keep track. So we're just going to do this stream, and we're going to use the read, and just type in the name of the file that I had you all download, which is BO82, which is the station name that I downloaded this from, and then EHZ, which is a channel of data. So that's all you need there because we're just reading it in from the same directory, hopefully, that you put this notebook in. And then we're just going to print out this stream so that we can see what's in it. So when you run that cell, you should see that we have one trace in a stream. So the way that streams work is that data, each line of data basically is included as a trace. So a stream kind of acts as a list of all of these traces of data. And these trace objects include data and the associated metadata that you would find, for example, on the IRIS website when you try and download the data. And we can grab a trace from a stream element the same way that you would an item from a list. So we're just going to call this trace TR, and we can just grab like the first index out of the stream because that's the only one that we have. And if we print that trace, you'll see that basically the exact same thing comes up. And within this line, you can tell the network, station, and channel of the data, the start time and the end time, the sampling rate, and how many samples there are in it. So we can go into this specific trace object and just view the data itself. So as you might expect, we're just going to call this variable data. And to grab it, you just get the property from the trace itself. So you just do tr.data. And if we print data, you can see that you end up with a NumPy array. So then you can use this NumPy array to do any of the kind of operations that you normally would in Python on NumPy arrays. And you can also really easily view the metadata that comes with this specific trace. And so all you have to do for that is do tr.stats. And if you run that cell, basically it gives you all of the information that is downloaded alongside the data from wherever you're getting it from. So you get the network, station, location, if there is one. There isn't for this particular example, channel, and then a bunch of other things that you might want to use at some point. And you can also...
There was a request if you could make the font on your screen a little bit bigger.
Sure. I think there's probably a way to zoom in here somewhere.
I think you can do, if you're on a Mac, Command+, and it will zoom in.
There we go.
Maybe perfect.
All right. Sorry, I didn't think about that earlier. Okay. So if we want to grab any of these particular properties out of the metadata, all that you have to do is add an extra dot after the stats, basically, and then the name of whatever thing that you're looking for. So for example, you want to pick out the network from this metadata. You just do and my keyboard again. You do tr.stats.network. And then let's say you also want to find out how many data points there actually are in your data. You just do tr.stats.npts. And when you run that, it gives you the network and it gives you the number of points. Another really useful thing that you can do with traces is you can make simple plots of them. So if you just want to get a really quick idea of what the data looks like, all you have to do is tr.plot and then parentheses after it, because this is a method that's acting on the traces. And what I like to do, just because this is a Jupyter notebook, is if you put a semicolon after the end of it, it won't give you a plot twice. So that's something you're going to see me do a lot in this notebook, just to simplify things.
Sydney, we have one other request. If you could slow down just a little bit.
Sure. Okay. So this is how you basically make a plot. And you can do some things with these plots in ObsPy to make them look more unique and plot different things. And I'm going to go over just one of the basics here, but you can find more information in the ObsPy tutorial pages online, which I've linked to in the notebook. And what most people do is take this data and make your own custom plots in Matplotlib. And that's something that I'm going to talk a little bit about later. So there's lots of different settings you can change just by putting things in the parentheses in this plot command, such as plotting different colors and changing how your axis ticks are formatted. And this can be useful if you're plotting multiple things at the same time. You can also make stacked plots of data that run for a long time using an example called dayplot. So that's something that you see posted online by different seismology groups a lot. And in this tutorial pages from ObsPy, you can get a lot of these different examples, but we're just going to do one where we change the color as an example to start out with. So this is pretty simple. We just do tr.plot again, and then inside the parentheses, all you have to do is type color equals whatever color you want. So I just went with blue. I'm going to stick a semicolon at the end again there, and then if you shift enter and run that cell, you get that same plot, just the trace is blue this time. So that's pretty convenient. And so far, we've only been working with just the one trace in this stream object, which has a single channel of data from a single station. But often you might want to work with multiple records at the same time. And you can accomplish this in ObsPy streams because they can hold multiple traces of data at the same time. And there's a couple of different ways that you can read in individual files to a stream one at a time. So the first way that we're going to do it is just with plus equals in Python, which some of you might be familiar with. So we'll just start out by reading in one of the other example data files that I put in Slack. So we are going to use read again, and then we'll just type in the name of this file, which is cwc_hne.mseed. And then in order to add an additional trace to the same stream, all you have to do is st plus equals read, and then we type the next name. So this is cwc_hnn.mseed. So here we're just reading in two different channels. This is east-west data and this is north-south data. And Emily next week is going to talk a little bit more about the naming conventions for these things. And then the last thing we're going to do is we're going to add in our vertical data as well. So you just type the name of the file again, cwc_hnz.mseed. And then all we have to do is similar to how we did before, we just print out st. And if you run that cell, now we can see that instead of the one trace that we were working with before, we have 3 traces in this stream. So we can see, again, start and end times are all the same, but we just have different channels of the data that we've downloaded. And another option that you can use to read in multiple files at a time is read them in as traces, and then ObsPy knows how to add them together into a stream. So the output is ultimately the same. You get a stream that has 3 traces in it, each containing the data and the metadata. This is just a slightly different way to do it. So for this first one, if we wanted to read in the first trace, we'll just call it tr1. And what I'm just going to do is copy the same line from up here because the function is exactly the same. So tr1 is just reading this cwc_hne file. tr2 will be the second one. And we don't have to do plus equals this time because we're not actually adding them to the stream yet. And then TR3 will be this last one here. So then to actually put them all in the same stream, all you have to do is ST equals TR1 plus TR2 plus TR3. And so ObsPy knows what to do with this. It knows when you're trying to add 3 traces together, it wants to add them all to the same stream. So if you print the stream and run the cell, you can see that you have the exact same result as you did from running the previous cell. You've just got 3 traces in it now this time. So there could be different situations where you want to read in data a different way. And this is just 2 options that you can do for these. And the exact same way that we made those plots, the simple plots of the traces before, we can also do this with streams. And it will end up plotting all of the traces on one plot basically that you make, that you put in the stream. So instead of doing st.plot or tr.plot, excuse me, we'll just do st.plot. And if you run that cell, you end up with this nice graph where you've got all 3 of the channels of data in one go. So one thing that you might notice about these plots, and I'll just leave this here in case you still need this command, is that our y-axis doesn't really mean anything. And this is because right now the units here are still in digital counts, which is what comes from the instrument itself. And we have to remove the instrument response to actually convert these numbers to some kind of meaningful measurement of ground motion. And I'll talk more in a bit about what the instrument response actually is. But the great thing about the availability of online seismic data is that responses can be downloaded right alongside the data. So let's talk about downloading data from online repositories. And for this example, we're going to use the IRIS Data Management Center. So IRIS in this case is just one client that stores data. And the other client options can be found at this link that I included here. And these are managed, naming and everything is managed by the International Federation of Digital Seismograph Networks. It basically helps coordinate digital or data access across all these different clients. So in order to start downloading our data, we have to import this client ability to choose where we want to get it from. So for this, we just type from, and then we're going to do obspy.clients.fdsn. And from that, we're going to import client, and make sure you have a capital C on that one. And then we just are going to set the client that we want to use in this case, which is IRIS. So we're just going to make this variable, we'll call it client, and we'll just type client with the capital C. And then inside of these quotation marks, IRIS. So when you run this cell, we're basically just telling this notebook, oh, I typed FSDN, make sure you type FDSN. There we go. So now basically we're just telling the client thing that we're wanting to download our data from IRIS. So the first thing that's important to know about downloading and handling data in ObsPy in general is how times are managed. And this is done using a class called UTC datetime. So the first thing to do to start working with that is we're just going to import that from ObsPy as well. So you just type, again, from ObsPy, import UTC datetime. And again, make sure your capitalization is consistent with what I've done here. And also spell things correctly is a good note, as we saw a minute ago. So UTC datetime objects are pretty easy to use, and the format is relatively easy to understand. But if you're like me and you sometimes forget exactly what that format is, you can check the ObsPy documentation again, which I've just linked here. So to create a UTC datetime object, you need a year, month, and day, or a year and a joule day. And all the joule day is basically is counting days of the year from January 1st being 1, and you just count up to 365. So it's just a different way that some places might record their data. So, and then you need a time and 24-hour clock with an hour, minute, and a second. So this could be the origin time of an earthquake, or just the start of any time period that you're looking to download data for. Then you just have to string them together in the right order, which I've included here in the notebook for working with month and day and working with joule day. So what we're going to do in this notebook is try an example from last year's magnitude 7.1 Ridgecrest earthquake. So go ahead and click on this link here if you just want to copy and paste it like I'm going to. And so when this is just linking to the USGS page for this earthquake. And what we're interested here is this box that says origin, because we're looking for the origin time of the earthquake. And if you click on this, it basically gives you a bunch of the information about the earthquake. So what we're interested in here is this origin time. So all you have to do is copy this time. You can leave the UTC part off. So if you just go ahead and copy that, and then we go back to our notebook. To create a UTC date time object, you basically only need that string that we copied and to put a T where that space was. So let's just create a variable for our time. We'll just call it time. And then you just want to initiate this as a UTC date time object. And then in the parentheses, all you have, or in the apostrophes here, all you have to do is copy and paste this, the time that we grabbed from the earthquake page. And just where this space is in the middle, put a capital T there instead. And then if we print our time and run this cell, you get this output that basically looks exactly like you put it in here, just with some extra zeros and a Z at the end. But now it's in this format that ObsPy can understand and work with. And another thing that's really convenient about UTC datetime objects is that you can just add and subtract a number of seconds from them to get different times. And this is useful when you want to download a specific segment of data. So let's say that we want to download the data from 1 minute before this earthquake's origin time to 15 minutes after it. Since we calculate in seconds, as you might expect, you can just multiply 60 for 60 seconds per minute times the number of minutes that you want. And you can do that again for hours if you wanted to download a really long section of data. So for the data that we want to download, let's call this variable start time, because that's when we want the data to start. And so here we already defined our time as a UTC datetime object, and that's what we did in the last cell. So if we want to download from a minute before that, all we have to do is subtract 60. And so this is going to tell ObsPy that we want 60 seconds of data from before that. So if we print out the start time here and run that cell, you can see that the output UTC datetime object we get here is 3:18:53, whereas the time we had before is 3:19:53. And so we can do the same thing for then the end time of the data that we want. So if you just type end time equals time, and we want 15 minutes of data after the origin time we said. So we can just do 15 minutes times 60 seconds per minute. And then if we print out the end time, if you run that cell, again, you can see that this is 3:34, which is 15 minutes after this 3:19 that we put in here. So we have the times basically for this data we want to download, which is going to be the magnitude 7.1 Ridgecrest earthquake. So the question is, where do we want to actually get the data from? We're going to need some kind of seismic station where we want to get this data from. So basically when you're downloading data, there's a standard called SEED that follows a convention for identifying data that's consistent across a lot of different things. And so what you need to follow this SEED standard is first a network code, which identifies which network data belongs to. And you can check out all the available networks at the IRIS metadata aggregator, which I've linked here, and it's something that you'll use in the lab. And network codes are unique and assigned by the FDSN. So there's no two networks that are going to have the same code. And then you have a station code. And this is a station, like a seismic station or something within a network. But these aren't necessarily unique. So if you want to identify a specific thing, you have to make sure you use the network code and a station code together. And then sometimes you'll have stations that have more than one instrument at them. And you can specify these different instruments using a location ID. So this isn't something you're going to see with every station, but it is common, especially with things like the global seismic network, where there might be a lot of different instruments at each station. And then finally, you have a channel code, which is a 3-character code talking about like basically which direction in your instrument you're getting the data from. And the way these are named is something that Emily will talk about next week. So the example that we're going to start with is choosing one network, one station, one location, so one instrument, and one channel of data from the Global Seismic Network Station in Tucson, Arizona. And the reason I picked this instrument is because it's the closest Global Seismic Network Station to Ridgecrest. So what you want to do is check out the MDA page, the metadata aggregator page for the Tucson station. So if you click on that link, it will open it up to the IRIS website. And basically here you have a bunch of different information about all of the instruments and channels of data that are available at this station. So you can see here it tells you the network is IU, which is the Global Seismic Network, and the station is TUC, which is this Tucson station that we want. And then if you look on this next part of it, you can see there's a ton of different location codes on the left here. And this is basically all the different instruments that are available. And these purple bars at the top are telling you what times the data is available for. So we can see that with this particular instrument, the data started being recorded on this instrument in 2017, and it goes until 2599, which basically means it's still currently gathering data. So in this case, we're just gonna stick with this top box because we know the data is currently running. We're gonna pick location code 00, which is this particular seismometer, which is down in a borehole underground. And we're just gonna start with this HH1 channel, which is gathering data at 100 samples per second. So I'll type all this in the other cell so you don't need to like have this page open. Basically, if we go back to our page for the Jupyter Notebook, we're gonna define each of these things, the network, station, location, and channel. And then we're gonna use these things that we defined to download actual data from there. So in this case, we're just gonna call the network net, and then you just have to put IU in the apostrophes. And this is telling you you want it from the Global Seismic Network. For the station, we put TUC in the apostrophes, and this is telling us we want it from the Tucson station, like we saw on the IRIS page. For location, we're gonna use 00, like we talked about on the IRIS page. And then for the channel, we're gonna stick with that HH1 data, sampling at 100 samples per second that we mentioned. So to actually download the data, we use a function in ObsPy called get waveforms, which does exactly what it sounds like. It gets the waveforms from you. So in this case, we're gonna call this ST again because we're reading in a stream of data. And all you have to do is type client and then .get _ waveforms. And then inside the parentheses, all you need to download this data are the network, station, location, and channel that we defined, as well as the start and end time that we also defined in our UTC datetime objects. So in here, all you have to do, because we defined these things already, is type net, stay, loc, chan, and then start time and end time. And I'll leave that up for a second in case you need some time to type it in. But you can also type these things directly into the get waveforms function if you want. I just choose to do it this way, especially because if you're running through like a list of stations or something like that, if you end up wanting to write this into a loop, it's easier to just have it defined like this so you can iterate through everything. So then we're just going to do the same kind of thing we did before, is print out the stream so that we can see what is actually in the stream. And then we're just gonna make a simple plot of it again so we can see where that earthquake is happening. So if you run that cell, if you spelled everything right, hopefully you'll end up seeing that you've got one trace in the stream. It's from this Global Seismic Network, the Tucson station, location 00, and then channel HH1. We've got the start time and the end time that we picked out, and we've got our 100 Hertz data with a total of 96,000 samples. And we see on this nice plot the earthquake happening right here. So the next thing that you might be interested in is, what if you want to download multiple channels of data? Because usually you're wanting to look at all 3 of them, or 4, or however many are in your instrument at the same time. And the convenient thing is that in ObsPy, you can use Linux syntax like wildcards to accomplish this. So in this case, instead of putting our channel, our chan is defining it as HH1, we're going to define it as HH star. So this will download all of the data available for this particular station and location. It will download all of the channels that start with HH and have something else in this final spot here. So then all you have to do is do the client get waveforms again. So what I'm going to do is I'm just going to copy this line, because we're basically just going to be typing the same thing again. And I'll put it right underneath where we redefined the channel. And then we're just going to do the same thing again to see what this looks like. We're going to print our stream out so we can see the 3 different channels of data that we downloaded. And then we'll just make a quick plot as well. So hopefully I've left that up long enough for you to get everything copied. And then we just run the cell, and we'll see now that we have 3 traces in the stream. They're all exactly the same except for the fact that we have HH1, HH2, and HHZ. So we have all 3 directions in the instrument. And then it's plotted this nice earthquake that we can see on all 3 channels here. So now we're going to go back to talking about how these numbers on the y-axis don't actually mean anything. Right now, they're just in this digital counts unit. It's quantitatively meaningless. Is that a question?
We have a question. So when using the wildcard to query channels, do they always return in vertical, horizontal order?
That's a good question. I actually don't know about that. That was probably a good question for Emily next week, because she works at the Albuquerque Seismo Lab where I did my internship. And they do a lot of management of the global seismic network and things like that. So I would save that question for her next week. Okay, so the next thing that we're going to talk about is how we remove the instrument response. Because right now we can't say anything about what's actually happening in units of ground motion on these plots. So I'm going to scroll down to the next section here. So the reason that we have to do this is because of the way that seismometers actually record data, which I'm going to give a super brief overview about. Because in seismology, we're interested in such a wide bandwidth of frequencies in the signals that we record, we've had to design our instruments to be sensitive to this entire range of frequencies, which isn't as simple as just having a mass on a spring. And the typical picture of a basic seismometer is an instrument that records the motion of the frame of the seismometer relative to a stationary mass in the instrument. But this only gives us a limited dynamic range over which we can record. And to increase this range, we have to use electronic feedback loops in the instruments. So instead of recording like the motion of the frame, we are basically recording the voltage necessary to keep the mass inside the instrument stable while the ground is moving. And every seismometer is hooked up to a digitizer, which converts this analog voltage signal to a digital record of counts that can be read by a computer. So when you download data from IRIS, what you're actually getting is a time series of counts from the digitizer that's attached to the instrument. So in order to convert to actual ground velocity or acceleration, we have to account for the digitizer and the response of the seismometer itself to ground motion, which is frequency dependent. So theoretically, this is pretty complicated and not exactly what I'm going to talk about in this tutorial. So I've linked this textbook chapter here if you're interested in learning about the mathematics and the derivation of that. But in practice, it's relatively easy to remove instrument response in ObsPy. You just have to make sure that you download the response with the data when you originally do that. So we're going to keep working with the same Tucson station and the Ridgecrest earthquake. But this time when we download the data, we're going to make sure we attach the instrument response to it. And so I've just copied from our earlier cell basically the variables that we already set. So just the same time, the same start time and end time, and then all of these different network, station, location, and channel. And for this example, we're just going to do it back on only HH1 to make it easier to understand what's going on. So go ahead and run that cell. And it's just, you know, basically redefining everything and making sure that we have a single channel instead. So the only difference now is that when we do this client.getWaveforms, we just have to add one additional option inside the parentheses here. And this is to tell getWaveforms to attach the response from to the data when you download it. So all you have to do is type inside the parentheses, attach response. And this is a Boolean thing, so all you have to do is say that it's true, that you want to do that. And then if you run this cell again, it's going to look exactly the same. We just have the trace in the stream, the single trace because we're only doing HH1 this time, and we have our nice plot of the earthquake data. You can't really tell anything's different, but the response is attached. And so one other thing to note when you're doing response removal is that the function that's in ObsPy acts on the data itself. So it's going to overwrite the original. So if you want to keep the original data, you're going to need to copy your stream first. so that you can do the removal on a copy of the stream instead of the original. So we're going to call this new stream that we're going to copy strem, just for remove. And then all you have to do to copy a stream in ObsPy is just do st.copy. So if we print out our new stream, strem, and st, which was the original one that we had, if you run that cell, you'll see that everything is exactly the same. So basically this is just showing you that when you copy a stream, it works totally fine. And so now we can perform this response removal on this strem, but still have our original st to compare with, which is useful. So now we're going to remove the response. You can set the units that you want the ground motion to be represented in using the output option in this. So if we just type strem, which is the stream that we want to remove the response from, the function is just conveniently called remove underscore response. And then inside the parentheses here, all you have to do is specify which output you want. So you just type output equals whatever particular thing you're looking for. So in this case, we're going to do velocity. But the other options, which I'll just put a comment here in case you want to try something else, is you can just use disp if you want displacement, and then ACC if you want acceleration. So now what I'm going to do is I'm just going to plot the original data so we can remember what it looks like, and then we'll plot strem as well so we can see what it looks like once the response is removed. And with this reminder that I've added down here is that if you run this cell multiple times without going back and doing this copying again, the output's going to look strange because you already removed the response. So you'd be trying to remove the response twice or 3 times or how many times you run it. So just make sure that if you want to rerun this cell and perhaps try a different output, that you're going to have to go rerun this copy one as well. So if we run this cell, this is the original data, and this is the data with the response removed. And the waveform looks exactly the same in this case, but you can see that the units on the y-axis have changed. So now instead of this digital counts here, we've got ground motion and velocity, which is meters per second. So this is good. I'll scroll back up here if you want to check out this cell any longer. But the reality is that the way that I did this is an oversimplification of the response removal process because data is inherently noisy. So if you're dividing data at low and high frequencies by a response, you can end up amplifying the noise a lot. So this is why bandpass filtering is commonly done as a part of the response removal process. And you can do this by adding additional options inside these parentheses here. And this is particularly important if you're using an instrument that doesn't have a flat response at a range of frequencies that this broadband GSN sensor does. So we can visualize what's happening in the response removal process by adding an additional option inside these parentheses here. So we're just going to go ahead and copy the stream again for the reasons that I mentioned before. So if we just type strem again, just call it copy this original stream, and then we're going to go ahead and remove the response again, but we're going to use this plot option here. So if we do strem dot remove response, same as last time, output equals, we'll keep it in velocity. All you have to do is put plot equals true. And then if you run this cell, it takes a little bit longer to run this one, but basically it gives you these 3 different graphs that kind of walk you through what's happening on each step of the removal process. So if in the case that you wanted to use bandpass filters or something in your response removal process, you'd be able to see how each of these things worked throughout the response removal process. I'm not going to demonstrate using filters in this tutorial because it can, as Emily put it, can be kind of a dark art, and it's a little bit tricky to choose what filter is appropriate for the frequencies that you're looking at. But this is something that Emily is going to talk about next week in her tutorial. So hopefully that's given you enough time to copy this cell down. But basically you can just see that in this case, these plots are showing the instrument response in this middle plot, which is in red. And then the data which is in blue. And if you had decided to do a bandpass filter or something, you would have this data be cut off at certain frequencies here. And then on the right, this would be showing you what happens after each step of the process to change the data. But in this case, since we didn't do any filtering, they all look the same other than the units on the y-axis changing from counts into velocity. So if we go back and just do our simple stream plot method with this plot, or this stream that now has the response removed, we just do strem.plot. It looks the same, just like we saw earlier, but now we've got meters per second instead of counts on the y-axis. So the next thing that you might want to do with this data is, now that the response is removed, you might want to save it into its own mini seed file on your computer so you can go back to it later, work on it, and load it into different scripts. And so you can do this with the stream.write function. So you basically, all you have to do is specify the path that you want to put the data in, a file name, and then the format. And so for this example, I'm not going to specify a path because I just want to save it in the same directory that this Jupyter notebook is in. But all you have to do is, let's establish our file name first. We'll just call this file name. And in this case, I want to have it named the same way that I named the files that I had you guys automatically download. So we're going to call it, we want to put our station name, and then we want an underscore to be in there. And then we want the channel that we also, for this data. And then we just need to add the file extension. So in this case, we're going to save it as a mini seed file. So the file extension for that is mseed. And then to do the actual writing of the file, we have to do strem, which is the stream that we want to write. And all you have to do is type write, the file name, and then specify what format that you want to save it in. And you can do this with SAC files or whatever kind of data format that you're looking for. You just have to type in whatever it is that you're interested in. And so in this case, we're going to do it as mini seed. Yeah.
Before we move on, I have a question, or we have
Sure.
a question. So the question is it safe to assume that the original counts are related to velocity, or how can I know if they correspond to acceleration in case of an accelerometer?
That's a good question. I actually don't know specifically, but I think there's a way, again, to look at it somewhere on the metadata page. And again, maybe I'll defer that to Emily next week, who knows more about this, how the data is organized, because I'm pretty sure there's a way to check that, but I don't actually know it myself. So sorry for that unhelpful answer, but hopefully next week, Emily can answer that. So in this writing process, you get this error in this case, and it just tells you that basically Anaconda is automatically choosing how the encoding is going to work. So this is something that I see come up a lot. It never really actually affects how the data is saved. So it's something that I don't worry about. And it maybe if you're on a different type of computer, this doesn't happen. I'm not exactly sure. But now that we've saved this data, if you pull up your file explorer, you could see that the data file is in there with the name that we set. And so what we can do now is we can just read it back in as a stream the same way that we did with the sample file at the beginning of the tutorial, and then we can mess around with it some more. So in this case, we're just going to call it ST again, keeping with the standard structure. And in this case, because we decided to name it after the station and the channel, it's just going to be called tuc_hh1.mseed. And so we can print out the stream the same way we did before. And we can do a little st.plot again, just to show that it really still is exactly the same piece of data that we've been working with at this time. So now I'm going to talk about some of the different methods that are available for working with streams and traces in ObsPy. And there's a number of different public methods that people have written. I'm going to go over a few of them that I use the most often. If there's anything else that you're interested in doing that I don't cover, I've linked to the ObsPy documentation for traces and for streams here. And there are some different methods available between the two different types of objects, but all the methods that I demonstrate here on this stream that we just loaded in, you can also use on individual traces if you don't want to do it on a whole stream. So the first thing that we're going to do that probably a lot of people do when working with seismic data is filter it. And this is if we wanted to look at a specific frequency range of data in like an earthquake or something like that, we can filter it to just look at those frequencies. And there are a ton of different filter options available in ObsPy, including band pass, band stop, low pass, and high pass, and some other experimental filters that people have written from papers and things like that. And so for here, we're just going to use the band pass example. And similar to remove response, the filtering operation is performed on the original data. So make sure if you want to keep that original data, that you make a copy of your stream first so that you retain it. So for our bandpass example, we're going to say that we're only interested in the data between, say, 1 and 20 hertz. And defining those filter limits is pretty easy in the option. So the first thing we're going to do, again, like I mentioned, is just copy our stream. So let's call this one st_filt because we're going to filter it. And we're just, again, going to do st.copy to copy this from the original stream. And then to actually do the filtering, you just do st_filt, which is the stream we want to filter, .filter. And then inside the parentheses, all you have to do is specify the type of filter that you're using. So in this case, that's bandpass. And then for bandpass filter, you want to have a minimum frequency and a maximum frequency where it's going to be cut off. And so our frequency, our minimum frequency here is just going to be 1 hertz. And our maximum frequency is going to be 20 hertz. And so the reason that I like to keep the copy with the original data is so that we can look at the difference afterwards. And so we're just going to plot the original data. And we're also going to plot the data that we've now filtered. Sorry, I called it filt, not filter. And then if you run this cell, you can see that, I'll try and keep that in there. You can see that we've got the original data here that has all this like lower frequency stuff going on. And then when we filter it so that we're just looking from 120 hertz, you can see that we've got a bunch of high frequency stuff happening. So this is just one quick example of how that you can filter data. And if you want, then you can now save this as its own mini seed file again, or you can just keep working with it, which is what we're going to do. So hopefully that's been long enough to see that cell. And remember, if you miss anything, we're going to upload the full notebook with all of this code at the end before the lab section, so you can fill things in then too. So something else that you might want to do if you no longer care about some of your data. So now if we look at this filtered one, we're not really interested in what's going on out here, or maybe even in front of the earthquake, because all the information we want is in this earthquake right here. So if you want to shorten stream and chop some of these extra pieces off, you can do this with the trim method. And for this method, all you need is UTC datetime objects for the time that you want your new trimmed trace to start and to end. So first, we're going to just take a look at the times that we used for this data, just to refresh our memories. And so if you remember from the beginning, we can look at the stats for a particular trace. And since a trace is just one thing out of a list in the stream, all we have to do is index the first trace in the stream and then do .stats. And hopefully this looks familiar. And basically we can just be reminded that the start time that we picked is this, you know, hour 3 minute 18, and the end time we picked is this hour 3 minute 34. And these are already conveniently in the UTC datetime format. So in order to pick a new start time and an end time, all we have to do is grab these particular values out of the stats and then add or subtract time from it the same way that we did before. So let's say that we want to chop, you know, 6 minutes off of the end of the trace where there's nothing really happening, and then 2 minutes off of the front. So all we have to do is write a new start time. And so the first thing we're going to do is we're going to grab this start time out of the stats here. So the way that we do that is similar to what we talked about before. You just grab the first trace, .stats, and then .start time. And we said that we wanted this new start time, we want to chop 2 minutes off the front. So we want this new start time to be 2 minutes times 60 seconds later than the start time that we picked originally. And our end time, you just grab it from the stream the exact same way, st0.stats.end time. And we want to cut 6 minutes off the end of the trace. So we want the start or the end time to be 6 minutes before what it originally was. So you can just do -6 times 60. So if you run that cell, we'll now have our new start time and our new end time. And so now we can go through and trim the data. And again, we're gonna have to copy this first so that we don't lose the original. So I'm gonna call this new stream st trim because we're gonna trim it. And so we're gonna trim this filtered data that we made before. So we're just gonna make a copy of this st filt that we made. So in order to do the trimming, all you do is type the stream name and then .trim. And inside the parentheses, all you have to do is again define the start time and the end time. And since we wrote that in the previous cell, you can just do start time equals start time and end time equals end time. And again, we're just gonna plot the filtered original one that we came up with in the last cell and this new trimmed one so we can see what the difference is. So we do st_filt.plot and st_trim.plot. And so if you run that cell, we can now see that we've got our filtered data that we made here with just the 1 to 20 hertz. And then if we scroll down, sorry, hopefully you copied that down, but you can see now that we've cut off a bunch of the data before and after this earthquake started. So it really kind of narrows us more to a specific time period that we might be interested in looking at. And you could save this again to a new mini seed file if you wanted to. And one option that I didn't use in this example, but you can do when you're trimming data is if you have any gaps in the data, like your instrument wasn't working for a minute or a couple samples or something, you can fill a value into here. And so I included this little snippet down here where if you go into the parentheses in your the trim function, all you have to do is add this fill value equals whatever number you want to fill, usually 0. And it will just add a 0 in wherever you're missing a trace. So if you have a really long time period where your instrument was broken, this may not be the best idea. But if you're just missing a sample here and there, that's one option that you can use. So the next thing that we're going to talk about is changing sampling rates. And this is the last stream and trace method I'll cover in this tutorial. And there are 3 methods in ObsPy for changing the sampling rates of data in a stream or trace. There's decimate, and I've linked all of the documentation here. There's decimate, so that downsamples the data by an integer factor that you set. There's interpolate, which increases the sampling rate by interpolating between the data points that you have, and there are a bunch of different method options for this. And then there's resampling, which resamples the data using a Fourier method. So I'm just gonna demonstrate decimation here because it's the simplest, but if you wanna use the other methods, just check out the documentation. And again, this operation acts on the original data, so make sure you copy it first if you want to keep it. So first, we're going to double check the original sampling date because you might not remember what it is if you downloaded this file a long time ago. And this will help you choose what factor you might want to decimate by. So first, we just have to go into the stats again. So remember, now we're going to use our trimmed data that we kept. We're going to grab the first trace out of that stream, and we do .stats. And then .sampling_rate. So if you run that cell, you can see that this is 100 hertz data that we downloaded. So a nice simple factor to decimate by could be 10. So let's try that. So I'm just gonna call this new stream that we're going to decimate st_dec. And we're first going to copy the trimmed stream that we made in the last method. And then to decimate, all it is you type the name of the stream and then .decimate. And in the parentheses, you put the integer factor that you chose. So in this case, we picked 10. And then similar to before, we're just going to plot both of these different streams that we now have, our trimmed one and the decimated one. And when you run that, you'll see that they really don't look different at all. The only difference is maybe on the y-axis, you've got some numbers slightly different here because it picked different points to retain, different maximums and minimums potentially. But the way that you can check to make sure that this actually worked, since the plots don't look too different, is you can just go back and check the stats again for this new stream. So if you do st_decimate, grab the first trace, .stats, .sampling rate, same as we did before, you can now see that your sampling rate is 10 instead of 100. So we decimated by a factor of 10 from 100 samples per second to 10 samples per second. So this definitely does not cover all of the available methods for traces and streams, and others that you might be interested in using that I've used before could be differentiating your data, integrating it, stacking, merging, sorting different traces, and many others. And if you're interested in using these, check out the ObsPy documentation that I linked at the beginning of the section, as there are lists of the different methods available, and you can click on each of them to see how to implement them. So the last thing that we're going to talk about in this tutorial is how to make some basic but nicer plots of our seismic data in Matplotlib, because there are many more customization options than just what you can do with this st.plot or method that we've been using. So the first thing we're going to want to do is make sure that we have our times and our data separated, because for any type of graph or plot, you're going to need an independent variable, which in this case is the times, and a dependent variable, which is in this case the ground motion records and velocity. And these two things are super easy to parse from trace and stream objects. In fact, at the beginning of the journal, if you remember, we already pulled out the data into a NumPy array. So let's just do that again, and we're going to go back to the unfiltered, untrimmed, undecimated data, back to our original stream. And so in this case, we're just going to, let's call this data again, same as we did last time. We'll grab the first trace out of the stream, and then you just do .data, just like last time, to get that data out of there. And then if you print data, you end up running it and getting this nice NumPy array. It's got ... in the middle, so you can see there's lots more samples that didn't get included, just to not plot 96,000 things in one go. And getting the times is slightly different, but also very simple. And the only difference is that instead of being a property of this trace, the times is a method that acts on the trace. And so to get the times, all you have to do is type times equals, grab the first trace, st0, and .times, and just add the parentheses afterwards like you would for any of the methods that we implemented before. And then if you print out this times, you can see that it's also this nice NumPy array. And so if you've used Matplotlib before, or just graphed anything in general, you know that you need to be able to plot something, you need the same number of data points on your x-axis and on your y-axis. So what we should do is check the length of these arrays to make sure that they're the same so that we can plot them in, more easily. So all that we're going to do here is just use a NumPy or a Python function called length. Keep using the wrong keyboard, that doesn't work. And so we'll check the length of the data array that we pulled out, and we'll check the length of the times array that got pulled out. So if you run that cell, you'll see they're both 96,000 samples long. So that should work perfectly fine for plotting. So in order to plot things in Matplotlib, you just have to import the library. So the way that I like to do this is to do import matplotlib. It's a little difficult to type the first few times. And then I like to just include this pyplot at the end here, and I import this as PLT. And this means that when you use this, all you have to do is type plt.plot or .scatter for the different methods of plotting that you might be interested in. And so if you import that cell, we're just going to try out a super, super simple plot first, because all we need are the independent variable and the dependent variable, the times and the data that we already pulled out. So if you do plt.plot now, put your independent variable, the times first, and the data second. And there we go. This looks basically the same as the st.plot that we did before. It's super simple, but now it's got a color on it. And we can see the data basically looks exactly the same. But as anyone who is familiar with Matplotlib will know, there are an insane number of different customization options you can use to make publication quality plots. And I linked the Matplotlib documentation at the beginning of this section if you want to learn more. But I'll just go through a couple of the things that I would do to clean up this plot and make it look a lot nicer with just a few lines of code. So the first thing that I want to do is redefine and re-pull back out our network, station, location, and channel. And this is because I want to be able to label this plot with where the data came from. And I like to define this outside of where you actually type in the title, because again, if you decide eventually to do this with more than one station or something, if you're running through a loop of a bunch of different stations, it's really convenient to be able to index the network and the station or whatever that you're using so that it automatically gives you the right title for each of the plots that are generated. So because we already looked at the metadata earlier, we know we can just pull the network, station, location, and channel right out of there. So we're just going to redefine all of those things that same way. So we'll just do network equals st0. So grab the first trace again, dot stats, dot network. For the station, it's basically the same thing, st0 dot stats dot station. For the location, you can probably guess st0 dot stats dot location, and the channel, which is st0 dot stats dot channel. So we've got those 4 things, and we're going to use them later in the cell to write the title of our plot. So the first thing we'll do again is just generate our basic plot that we came up with last time. We do plt.plot with the times and with our data. And then, so one thing that I don't like about this plot is that we've got this extra blank white space at the beginning at the end. We don't really care about that because there's no actual data there. So we can put some X limits on our plot to, cut those out basically. So if we remember what we had for the number of samples, which was 96,000, if you know that you have 100 samples per second, you just have to divide this 96,000 by 100, which gives you 960. And that's how many seconds of data we have on this plot. And you can see that this kind of ends somewhere around the 960 range. So in order to put this X limit on here, you just do plt.xlim, and we're going to say we'll start at 0 and we'll end at 960 seconds. Another thing that you want to do with all of your plots is make sure you have labels on the X and the Y axis so people know what they're looking at. So to add an X label, you just do plt.xlabel, and then inside quotation marks, you just put whatever you want that to be. So in this case, our X axis is times in seconds. And then for our Y label, you just do plt.ylabel. And in this case, because we set our variable to be velocity earlier when we removed the response, we're just going to call this ground velocity. And we're going to specify that it's in meters per second. And the last thing we're going to do is the reason that we defined the net, station, location, and channel again. And this is to add a title. So to do this, you just do plt.title. And I'm going to call this the M7.1 Ridge Crest Earthquake, because that's the data that we downloaded. And in order to specify exactly what station and channel and whatever this data came from, all you have to do now is add these extra pieces that we defined up above. So the way I'm going to do this is I'm just going to put a dot between each thing. So we're going to add the net. So this shows up as an IU. We're just going to put a dot in between them. And then we add the station, put a dot. We'll add the location, put a dot, and we'll add the channel. And then I'll just put another semicolon at the end there. And so when we run, if we run this cell, if you typed everything correctly, now we have this plot that already looks much nicer. We've got labels on our X and our Y axis. We've got a title. And here you can see that we've specified the network, the station, the location, and the channel in the title. And so again, just to explain, the reason that we did that I defined everything this way is because if you, for example, have a list of different stations and you've written a loop to go through and plot the data from each station, all you have to do is index this trace number right here, because if they're all in the same stream, and then as it goes through, it will plot the correct network, station, location, and channel in the title of your plot. So I just find this to be a really simple way to label your plots and make sure that you understand what you're seeing if you go back to the plot sometime later. So hopefully that's given you enough time to copy down what we did in that plot. And something else that you might want to do in Matplotlib is plot the data from 3 channels from the same instrument at the same time, just the same way that we read everything in before. And we can do this in Matplotlib using subplots. So just to avoid confusion, because we've done a lot of different things here, we're just going to go back and re-download the data from this earthquake and do all 3 channels now with this wildcard that we talked about before. So all I did here is I've just copied the same things from above again. We've got the same time that we defined before, network, station, location, and channel, just now with the wildcard. And then we're just using this st get waveforms again. attaching the response to all 3 of the channels now that we're downloading data from. I just printed out the stream here to make sure that everything works fine. We're removing the response with the velocity output again, and then we're plotting this at the end to see what it looks like with our simple st.plot method. So if you run this, it might take a second depending on how fast your internet connection is, but you can see again that we've got all 3 of the traces with the 3 different channels in our stream here. And then we've got this nice plot, and you can see based on the units on the side that our response removal worked properly, and we've got everything in velocity, and we have all 3 channels here. So now we're gonna go ahead and make our fancy custom Matplotlib plot, and we're gonna put each of these 3 channels on their own subplots. So the first thing that we have to do here is separate each trace's data and times out. And so if you plot them individually, you can double check and make sure which trace in the stream corresponds to each channel. So this kind of relates to the question that was asked earlier about how you make sure which order things are downloaded in. And because I didn't know the answer to that question, what I've done in the past is just plot each of the 3 traces individually to make sure I know which is correct. And so in this case, we're gonna grab the first trace and plot that. We're gonna grab the second trace and plot that. And if you're more custom with MATLAB, remember that Python counts from 0. So the first trace is 0, the second trace is 1, the third trace is 2. So if we do all 3 of these things, basically then we've got our own plots that come up in order. So we can see that the first trace corresponds to this HH1 channel, the second trace corresponds to HH2, and the third trace corresponds to HHZ, which is the vertical data. So we can then, remember we did at the beginning of this section, we have to pull out the data and the times separately because we need each of those different NumPy arrays in order to plot them in Matplotlib. So this is going to involve some copying and pasting in this cell, but I'm just going to make sure that I name the variables properly so you can tell when you're plotting later which is which. So the first one we're going to do is just the first channel, or the first trace, which we just identified. So I'm going to call this first one HH1 data. And the same way that we did before, you just grab the data right from the trace, and then HH1 times would be using the times method on the same trace. And so, whoops, that should be times. There we go. And so now basically to do this with the other ones, because we're only just changing a couple of numbers, I'm going to copy this and paste it here. And so our next channel is going to be HH2 for each of these. And remember to also change this. You want a 1 in here to make it the second trace. And then if we just copy it again, or paste it again, in this case, now our third one is going to be HHZ, and we're grabbing it from the third trace in this stream. So if you run that cell, basically, I didn't print out the NumPy arrays for you. You could do that if you want, but now we have all of our data and our times separated into their own arrays. So we can start plotting. The first thing that we want to do when you're working with something in subplots is making a big like main figure basically, and then we add subplots and then add the data to each of them. So the first thing that I'm going to do is type this figure. I'm just going to call it fig, and you just do plot.figure. And for now, we're just going to leave these parentheses blank. There's different setting options you can do, which we'll talk about in a second. But if you run that cell, basically, it's just telling you you've got now this nice little figure, and we're going to go ahead and we're going to add some data to different subplots. So the way that you define subplots in Matplotlib, for each iteration of the subplot, you list the number of rows and the number of columns you want, as well as which one you're on. So in this case, what we're going to do is try and basically copy something like this, where we want 3 different plots. So the way this is set up is we have 1 column of plots, but 3 rows. So the first thing we're going to do, you just type plt.subplot. And then the first thing you put in is the number of rows of plots, which is 3. Then the number of columns of plots, which is 1. And then the one that you're working on. So in this case, we're working on the first subplot or the top one in the list. And on this subplot, we're going to put our HH1 data. So all you do is type plt.plot, add your HH1 times, which is the independent variable, the HH1 data, oops, make sure you put a 1 there, which is the dependent variable. And then we basically do the exact same thing with the other two subplots. So for this one, you do again, plot.subplot, 3 columns, 1 row. And in this case, we're working on the second subplot. And for this one, again, I'm just going to grab this plt.plot line and copy it because it's going to be basically the same down here. And just change it to be your HH2 times and your HH2 data. And then our third subplot, we do plt.subplot. Again, 3 columns, or 3 rows, excuse me, 1 column, and then we're working on the third subplot. And you can just paste that same line again and just change it to HHZ instead of HH1. And so if you run that, I'll make sure I forgot to put the semicolon at the end, we can see that it worked. We have the 3 different subplots with each of the data from each channel on here, but it's just really messy. Everything is squished together. So what we're gonna do is we're gonna make the figure bigger. And so in this next thing right here, this next box, I've just copied the same thing that we did before with the subplots and with defining the figure. But this time, instead of leaving the figure, the parentheses here blank, we're gonna specify a figure size in inches. So for this, all you do is type fig size, and then inside parentheses, you put first the width that you want in inches and then the height. So we're gonna make this like an 8 by 10 figure. So if you run this cell, automatically that looks a lot better. And it took some playing around to get a size that's right, so you can just try different numbers until you get something that works for whatever you're doing. And so now we're gonna go through and we're gonna add some more things to this, just like we did with the previous example, because we need some labels, and it would be nice maybe if we got rid of these white spaces and we changed the color on these different plots so that it's more explicit. Another good thing would be to include labels. So that's what we're gonna do in this next cell. And I know we're going a bit over time, but there's just a couple more things that we're gonna cover. So hopefully you can hang with me here, and then we'll have a break before we start the lab section. So the first thing we're gonna do is, again, we wanna add a title. So in this case, because we have subplots, we're gonna do this plt.subtitle instead of regular title. And we're gonna call it the same thing. So M7.1 Ridge Crest Earthquake. And we're gonna add the same style of title as we did before, where we're gonna include our network with a dot. We'll include the station with a dot. And then we're just gonna put the location, because now we've got 3 different channels, so it wouldn't make sense to identify the channels in the title of the plot. And the only other difference I'm gonna add here is I'm going to make the title extra large. So we're gonna define a font size now too, after this actual naming of the title. And let's call this a font size of 20. So this makes it nice and big. The next thing that we're gonna do is the same thing that we did earlier with grabbing all of the, or putting together all of the subplots. So the first thing, plt.subplot again, and we're starting with 3, 1, 1, the same as we did last time, 3 rows, 1 column, and we're working on the first subplot. So in this case, you start out the same way, doing plt.plot, and we're gonna put our HH1 times, our HH1 data, and then what we're gonna do here is we're gonna add an additional thing as a label. And what this will do is then when we initiate a legend later, it will label this particular subplot as being HH1. And this is convenient because now we want to know which one each of the subplots are. And the other thing we're going to do is we're going to pick a color for this. And so in this case, Matplotlib has a bunch of kind of default colors that are C0, C1, C2. That's just what I'm going to use for this example, but there is a ton of different color options that you can look up in the documentation if that's something that you want to try. So then, similar to before, we're just going to do our plot, or add our X limit. We're gonna go 0 to 960. And then in this case, we're just going to add a Y label, because if you look at this plot that we have here, since there are 3 stacked on top of each other, we don't necessarily need to put an X label on the top 2. We can just put that on the bottom one. So we'll just add a Y label, similar method to before, if you can spell it right. There we go. And we'll just call this ground velocity in meters per second again. And just to add an extra little feature, we're going to make the font size of this one bigger as well. So, and then the only other thing we're going to add is we're just going to do plot.legend, and just leaving these parentheses blank is fine in this case because we put a label up in the plot option here. So now we're basically going to do the same thing for the other subplots. So just for simplicity's sake, I'm going to copy this because we're going to be keeping a lot of the same stuff in each of these iterations of the subplots. But we just have to make sure we change the right numbers so that we're getting the right data plotted on this next one. So in this case, make sure to change the first part to a 2 because we're working on the second subplot. You want to change HH1 times to HH2 times. You want to change the label to HH2. And you want to change the color to C1 instead of C0. So this is just the next iteration in the color list that Matplotlib has. But we're going to keep our X limits the same, our ground velocity label the same, and we can also just leave this legend the same. So then if you paste that for a third time, all you have to do on this one is change this. So we're working on the third subplot iteration, change everything to HHZ instead of HH1. And in this case, we're going to pick color C2. And in this case, because this is the bottom plot, we are going to add an X label. So I'm just going to put this after the Y label part. We'll just call this plot.x label. And similar to what we did before, we're just going to call this times in seconds. And we're also going to make this the same size as the Y label that we made, which is 14. And if you missed any of that, this will be uploaded in a couple of minutes before we start the lab section. And I forgot to put the semicolon. And there we go. We've got a nice big title telling us that this is from the Ridgecrest earthquake. It's network IU, which is the global seismic network, the Tucson station, and all this data comes from location 00. And then we've got a nice plot now where we have each subplot is a different color. We've got labels telling us which channel each of this data is coming from. And we have nice axis labels on the y-axis and on the x-axis. And there are ways to make this even better in Matplotlib. So other things that I might do is move these plots closer together so you can just get rid of the X ticks because you really only need them on the bottom. And you could also make just one label for the y-axis since they're all the same. And you can spend hours making plots look perfect in Matplotlib from experience, I know that. And there's one final useful thing that I want to talk about, which is code provided by Liam Tony, who's going to be teaching the PyGM tutorial in a few weeks. And this is plotting so that instead of having times from 0 in seconds along the bottom, you have times on the x-axis in UTC times. So this is the last thing we're going to be talking about here. And so to do this, we just need an additional Matplotlib piece called dates. And so if we do an import matplotlib.dates as mdates is what we're going to call this. If you run that cell, I'm just going to demonstrate this on one channel for the sake of time. And the only difference here is that when you're grabbing your times out of the data, instead of leaving the parentheses in the method blank, we're going to specify a type. So in this case, because I said we're only going to work with one channel, we're going to go back to having channel defined as just HH1 instead of HH star. And let's call this HH1 times underscore MPL so that we're specifying that we're using this different Matplotlib formatting this time. And so the method is basically the same. You grab the first trace out of the stream, you do dot times, but then in the parentheses, the only difference is you specify type, and you can just put Matplotlib in the quotation marks. So if you run that, nothing happens, but we've just defined these new times. And much of the plotting here is exactly the same. It just incorporates another Matplotlib capability where you build your axes manually. So some of the syntax looks a little bit different, but the functionality is basically the same. And the documentation for this axis thing is here, which you can check out later if you'd like. So the first thing we're going to do is similar to how we defined figure before, we're just going to do add axes. And we're going to specify that we're making this as a little subplot instead, so it's going to be smaller. And then similar to how we did plt.plot before, we're going to do ax.plot. And then we have to specify our independent variable and our dependent variable again. So in this case, it's going to be HH1 times underscore MPL, the new time that we picked. And then we're keeping the same HH1 data. To set our X limits, here, because we're not using seconds, we're just going to do ax.set_xlim. And then we want the time limits on here to be the first time in our times arrays and the last time in our times arrays. So the way to do this is just hh1_times_npl, and we're grabbing the very first time from that array, and then hh1_times_npl, and we're grabbing the last time from that array. And that's what the -1 is for. Then we're just going to add some labels again. For the X label, it's just ax.set_X label. And in this case now, instead of seconds, we're going to have this be UTC time. And then we're going to set the Y label with ax.set_Y label. And we're still going to call this ground velocity in meters per second, because that's not changing. And then we're going to set a title the exact same way as we did before, with ax.set_title, magnitude 7.1, ridge crest earthquake. And then we'll just add our network plus dot plus station plus dot plus location plus dot plus channel, because we're again back to only using one channel here. So if you run this cell, I spelled something wrong. I put yable instead of y label. I'm just going to fix that. Also, I'm going to add a semicolon at the end because I didn't do that before. And there we go. So now this plot looks basically the same as the one we had before, but you'll notice that we have these weird looking UTC time numbers on the bottom. And so we need to make these dates something that's actually useful. And we can do this with a locator in Matplotlib. And you can read more about this in the matplotlib.dates documentation that I linked above. But basically what these 2 lines of code that I'm going to add does is allow Matplotlib to pick the best locations for the tick marks. So like, you know, a specific minute or a second or something, depending on the data. And it's going to let it automatically also pick the best format for these. So I just copied the same code that we just typed down into this box here. And so the only thing we're going to do is we're going to add 2 lines. So first we're going to specify a locator. And the syntax for defining this is again kind of complicated, and I would just check out the documentation, but basically you do ax.x-axis.set_, probably shouldn't type underscore as a word, set_major_locator. And then in here, you just put mdates, which is the package we imported earlier, and then set this to be auto date locator. And make sure you just add these extra parentheses in here at the end. And then we just need to tell Matplotlib to use this auto date locator on the x-axis. So you type ax.x-axis.set_major_formatter. And then we use mdates in the parentheses .concise date formatter. And there are other options, again, if you check the documentation. And then inside the parentheses here, we just use the locator that we set before. So if you run that cell, now that you can see that instead of these random numbers along the bottom, you've got UTC date time in hour and minute, and then it tells you what date this data occurred on, which was July 6, 2019. So that's all that I'm going to cover in this lecture portion. Apologize for going a bit over time. We're going to take a 5-minute break, I believe, and Francisca's going to stop the recording. And then we're going to go into the lab portion. So that was the other notebook that I had you guys download. So I hope that this notebook serves as a good introduction for you into ObsPy and working with